Okay, are we recording? Yes. Okay, good afternoon. So today we'll be talking about unconstrained multivariate optimization. A model for the unconstrained general nonlinear programming problem is as shown over here, where we have a minimized some function without any constraints. The only constraint is that this vector, which can be represented by x bar, belongs to the space R to the power n. Other than that, there's no other constraint over here. So as I was saying, our objective is to solve for all the values of x1, x2, x3 up till xn that satisfy the restriction. And the restriction is that it should be in the range of the decision variables, which is Rn. And we want to minimize the functional value. That means f of x bar. Okay. So to quickly begin with and to make sure to see whether you guys have actually studied this before coming today, let me give you a quick example and I want you to solve this for me, okay? I will ask someone randomly, okay? So if we have a function f of x, I think we can type, that would be easier. Okay, so what I want you to do is, I want you to find the maximum or minimum points of this function, which I have fx1, x2. So obviously this is a multivariate function, which is x1 to the power 3 plus x2 to the power 3 plus 2x1 to the power 2. Let me multiplied by x1 to the power 2 plus 4 multiplied by x2 to the power 2 plus 6. Okay, so I've given you this function. You guys can see this function?
Yes.
Okay, so what I want you to do is I want you to find the maximum minimal points of this function. So obviously what you have, first thing you have to do is you have to use the necessary and sufficient conditions, right? And we know the necessary and sufficient conditions for a univariate case. We know that the first derivative should be equal to 0 and the second derivative tells us actually whether it's a local minimum or the nature of the point, okay? So for this, I want you to do it because I've already told you that when it becomes a multivariate, how do we generalize the necessary and sufficient conditions? So instead of taking the, if you want to find the necessary condition, what you have to do is you have to take the first order partial derivative, right? So you have to take the first order partial derivative of this function. That means you take it x1 and first order partial derivative with respect to x2 should be both equal to 0, right? Am I right?
Yep.
Okay, so tell me what are the points?
Zero. Oh, no.
There is a proof, as you know, that we can prove the necessary and sufficient conditions using Taylor series expansion. We did that for the univariate case. For the multivariate case, also there you use a Taylor expansion. It's a bit lengthy, and I do not know whether we have it in our lecture notes or not. Oh, yes, I think I have it. I don't know. Oh, I don't have the proof. No, I don't have the proof. I've just said that. Well, okay, then let's just skip the proof. But let's assume, so I've actually mentioned the necessary and sufficient conditions over here for optimality. So for this guy to be a local minimum, what we have to have at this point x star is that the functional value should be less than equal to f of x, okay? Such that the distance between these 2 points, is the Euclidean distance, is less than some delta, okay? And it's a strong local minimum if it is just strictly less than, okay? And then we have the necessary condition. So the necessary condition is also given over here, that this point is said to be a local minimum if the derivative or the gradient at that point is equal to 0, okay? This can be, this can be a this is our critical point. So this can be a maximum, a minimum, or a saddle point. So in order to ensure which one of it is, or what I call the nature of that critical point, we use the second order check, which is the second derivative check or the sufficiency condition. And the sufficiency condition says that not only should, so the first should hold, that means that gradient should be equal to 0, and the Hessian of that should be positive definite, okay? So with that in mind, did you guys work out this example over here? The example which I gave you, you can do it at home. It's a very simple one. So what you have to do is take the partial derivative with respect to x, equal it to 0, and you take the partial derivative with respect to, I'm sorry, x1, equal it to 0. Take the partial derivative with respect to x2, equal to 0. You will get your points x1 and x2, okay? And then if you want to check whether it is a minimum, maximum, or saddle point, you write the Hessian for that function. Okay, we will look at examples ahead, and you just do the same for this guy. Now let's look at this example that I have already provided in this lecture note. So for those of you who have taken courses on, I don't know, machine learning or pattern recognition, you should know what is least square. Least squares, okay? So finding the least squares between of a function, okay? So we are given a function, all right? And we are given a function. The function is y is equal to a plus b divided by x, okay? And we want to find the best fit for this, and we're given 3 points, 1, 6, 3, 10, and 6, 2. So we want to see what are the values of a and b such that this would be the best, the least square fit. So what we have to do is we have to minimize some function f, which is basically the function minus the point yi, okay? So what you do is, so you have x minus I over here, and so you have this function. So basically what you're doing is a plus b divided by x minus y is equal to 0. So you want to minimize this. So you're taking the least square. So that's why you square it, and you're given 3 points. That's why you check it at all these 3 points. The function that you want to minimize, or your optimization problem, is this. So this is an unconstrained multivariate optimization problem. So how do you solve this? So what you do is you have to expand this. So you put the values of these 3 points. This is x, y, x, y, x, y. Put it in this. That means when you open up the summation, you would get this function. So basically, this would be the function that you want to minimize. Is it clear, everyone?
Yes.
Good. So I'm hoping you guys have gone through this, because this is something that I expect you guys to have already done. So what we do is, first thing is we check the necessary condition. That means the gradient should be equal to 0. Gradient is basically just the partial derivative, first order partial derivative with respect to a. Okay, so you take f partial derivative of f with respect to a, because we have a and b which are unknowns over here, and not x and y. We want to find a and b for which this function is minimized. So the partial derivative of f with respect to a gives you this, with respect to b gives you this. You solve for this, so you have 2 equations and 2 unknowns, so you can solve it, and you will get a and b to be this. When you get a and b and you put it back into this function f, it would give you a functional value of 30.86. So what you do is you say that the best fit for this guy would be a, because the function is a plus b divided by x. So you get a, which you got here, plus b divided by x would give you the value of 5. So this is the best fit function. Now we want to check whether this a and b that we have obtained over here after the first check, first order derivative check, whether this is a maximum or minimum, whether it minimizes this point or it is a maximum point, because we want to find the minimum, right? So what you do is you now take the Hessian. So when you take the Hessian, that means the second order partial derivative. This would be the Hessian matrix, which would be a square matrix. And you substitute whatever you get with this A star and B star that you obtain here. When you do that, you would get this matrix. And so we have already studied about Sylvester's check. And Sylvester's checks helps us to quickly find whether this Hessian is a positive definite or not. So we take the, what is this called? What was that called? Minor principles, okay? And so you have a 2 by 2, so you'll have one minor principle of dimension 1, 1, which is 6, and another minor principle of dimension 2, 2, which is the whole matrix. So taking the determinant, if both of them are positive, this is positive, therefore this is positive definite, okay? So we check that, okay, so since this is positive definite, then definitely A and B are a minimum. So if it minimizes the function. So this function value would be the minimum function value, okay? Now, with that said, there are some things that, I had written the proof using the Taylor expansion, but let's skip that because I can scan it and I can upload it so you can check it out yourself. Okay, but the proof is not that difficult. Okay, so basically about the sufficient condition, I need to again repeat that at the extreme point, that means at the point or critical point that you find, if the matrix of the second partial derivative, that means the Hessian matrix, is positive definite, then that point is a minimum point, okay? If it is a negative definite, then it is a maximum point. I will explain to you I'll give you definitions for positive definite, negative definite, positive semi-definite, and negative semi-definite shortly, okay? That's very important. You have to take notes. And so if it is negative definite, then it is a maximum point. Otherwise, if it is indefinite, that means not positive definite or negative definite, then it is what is known as the saddle point, okay? So to understand this, we need to know the Hessian matrix, which I already told you. It is taking the second derivative. So a Hessian matrix of size of 2 variables, A and B, would be as such, as shown over here. So you can generalize it for n number of decision variables. Okay. Then what else should I say? And also, okay, so now let me get to the definition of positive definite, negative definite, positive semi-definite, negative semi-definite, okay? So this, let me get to this later on. Let's go back here. File, new, don't save. Okay. Let's see. So now let's have the definition for positive definite. I'll call it PD just to save us time and to save me the effort to write so miserably. So a square matrix is said to be positive definite. This is PD. If the principal minor determinants, okay, so let's say our matrix is A, okay. So if the, what is this called? Let's say it is A n of dimension n times n, okay. So if the principal minor determinants of A are all greater than 0, okay, that means the determinant of A1, which is the submatrix of A with dimension 1, 1, is greater than 0. Okay. The second principal minor determinant is greater than 0 until and since it's of dimension n, the entire matrix A of n, the determinant of that is greater than 0.
Sorry, Professor.
Yes, sir.
I think it's leading principal minors because there are all other principal minors. We take only those that are upper left corner.
Yes, upper left. So
leading principal minors.
Okay, leading principal minors. Yes, probably you're right because I don't remember the terminologies. But what I mean to say is, let's say okay, now I understand why you're saying, because you can also take it from the middle. Okay, yes, leading principal minors, and thank you for correcting me. We do this, and this goes to A1n, right? And this is A21, A22, and this goes till A2n. And we have this going down till AN1, AN2, and it goes to ANN, okay? So this is our matrix. So our leading principal minor determinants would be, so if I want to say A1 is basically the top left most element. So the first row, first column element, okay? So what our friend was trying to say is that you do not take this guy or this element, you take the top leftmost. So you start from here. Then A2 would be top leftmost. So take the two, so submatrix, which has order 2, 2, okay? So you do not take, like, for example, let's use a different color. You do not take these two. These two is not the leading principal minor determinant, okay? And you do this until you take the entire, what is that, entire matrix, okay? Thank you. So this is known as positive definite. So if the leading principal minor determinants of A are all greater than 0, then it is that function that Hessian matrix or that square matrix is a positive definite matrix. Okay. Now, what is negative definite? Let's write negative definite, which I denote by ND, is the leading principal minor determinants of A, of this matrix A. It should satisfy this. So I should have minus 1 to the power k times the determinant of k should be greater than 0. Okay. So, and what is k over here? K is obviously 1. Sorry. What happened? K is equal to 1, 2, ... n. Okay. So if k is positive, this guy would be negative. Therefore, the determinant should be negative in order to be positive. So negative times negative would be positive. If k is even, if k was odd, this would be minus 1. And this should also be, the determinant should also be a negative value, so that minus 1 times a negative value would be positive. If k is even, then this would be even, and therefore the determinant of ak should also be positive. Therefore, the product would be positive, okay? So if it satisfies this, so starting with, so initially remember, k is 1, so it should be minus the determinant of ak should be greater than 0, okay? If this is the case, if it satisfies this for all k values, then it is a negative determinant. Is it clear, everyone? Please keep this in mind because this may be in your exam. The third case is...
Sorry, may I ask?
Yes, sir.
The top left determinant or corner means that, for example, A3 means it's 3 by 3 matrix. The determinant
yes,
of 3 by 3
A3 would
matrix.
be, so A3 would be A11. So A3, let's write it down. So when I say A, taking the determinant of A3 would be taking the determinant of A11, A12, A13. Then you go to A21, A22, I'm not writing A23, A31, A32, and A33. Okay, so you start from the top
Okay,
leftmost and you take the matrix of the dimension k by k. Okay,
yes, thank you.
good. So now let's go for P. What am I doing? Oh, this pen is okay. Now I'm going to write what is the definition of positive semi-definite. A semi-definite I'll write as ST. Okay, so positive semi-definite is defined as a matrix is said to be positive semi-definite. A square matrix is said to be positive semi-definite if the leading principal minor determinants of A are non-negative. What does it mean? It means that determinant of AKs are, so you have this, so it's the same as this PD, but you have this equality sign. So it could also be equal to 0. Okay, and over here, obviously, k is from 1 to n. 1 to n. Is it clear? Everyone?
Yes.
Yes.
Oh, okay. Now okay, then let me write it here. And finally, I think we have just one more left, and the other one is the fourth one is negative semi-definite. Can anyone tell me what's the definition? What remains? It's the case when all the leading principal minor determinants of A satisfy the same condition as negative definite, except that you have that to the power k, except that you have
Greater or equals to 0.
Yes, sir. Good. Greater than equal to 0. Okay. So if you do this test, okay, and if you check for all of this, so this is the Sylvester's test. This is the complete. What I told you earlier is just how to find PD, but now I've shown you the general for all the cases. So if there is a case which you find the leading principal minor determinants of the matrix, and you see it doesn't fit in any one of them, then that matrix is indefinite. Okay. So if it doesn't satisfy any one of it, so it is an indefinite matrix. And when a matrix is indefinite, that means that point is a saddle point. Arasha? So now that we have said this, is this clear, everyone?
Yes, yes.
Okay,
Just
now,
clarify.
you have a question?
Yes, yes. Why did you square 81, 82? I mean, that square in red. Didn't you said?
No, I said this is wrong. The one in red is the reason why our friend, he corrected me. He said that I should say leading principal minor and not principal minor, because this is also principal minor, but this is not the leading principal minor. The leading principal minor is the principal minor which starts from the top leftmost corner. So the blue ones are correct, but the red one is not correct.
Yes.
Okay.
Okay.
Good. Now let's make a new, and now I'm going to give you guys an exercise. Let me see if you can solve it. So I'm giving you a function, and actually, in theory, if you go to the mathematical proof and definition of the second order partial derivative, you see that actually the Hessian that we obtain is of a quadratic form, and I'll tell you what it means. So with this example, so suppose we have 10 times x1 to the power 2 plus 2 times x1 times x2. You guys have to work this out for me, okay? So x2 to the power 2. I've given you this function. It is a function with two decision variables, x1 and x2. And what is meant by it is a quadratic. That's why I've written q of x, because this functional value can be written as a quadratic function. And the quadratic function, if you write it in terms of matrix, this is how you can actually write this or represent this. So writing this is the same as writing. So this is the same as, I can say x1, x2, okay. And then I have my matrix, which is holding the coefficients. So we have 10, 1, this is symmetric. And we have x1, x2. Okay. So I can write this equation 10x x1 square plus 2x1 x2 plus 4x2 square in this form. Okay. And so this guy is actually the Hessian. And you don't have to know this. I'm just saying that you can write it in a matrix form as such. And this is a symmetric. That's why it's called quadratic matrix form. Anyways, now what I want you to do is I want you to tell me whether this Q of what type of matrix this Q of X is. Is it positive definite, positive semi-definite, indefinite, what? Quickly, 2 minutes. I've already given you the Hessian, so you have the Hessian. The Hessian is already this matrix that I've written for you, okay?
Positive
if you want,
definite.
I'm sorry?
Positive definite.
Good. So yes, just 1 minute. Let me just say this before I forget. So I've given you a function with two variables. You can take the, you can calculate the Hessian matrix of this by writing the Hessian matrix. You know, first element would be the second order partial derivative with respect to x1. Then the next one would be x1, x2. Then the element below this would be x2, x1, and this is x2 square. Okay. So you would get this, and then to find whether this what type of a matrix this is, as our friend said, this will be positive definite. That's because if you take this is Q, so let's say Q1 is equal to this guy, right? 10. So 10 is greater than 0. Okay. So you have to take Q2. Q2 is the whole matrix. So you take the determinant of 10, 1, 1, 4. And this would be what? 40 minus 1, which is 39, greater than 0. So since both of them are greater than 0, it satisfies the first condition, which is PD, positive definite. Okay, guys?
Yes.
Okay, now I want you to do this for me. This is something that I want you to do, and I'll give you 5 minutes. It will take more time than this. Oh, okay. Let me actually write with this pen. It's much more easier. Now let me just type it 1 second. Okay, so this is what I want you to do. So I'm giving you a function now, f of xy is equal to x to the power 3 plus 3 y to the power 2 plus 3 x to the power 2 plus 3. Why do we have y to the power 2? Is that correct? Let me check 1 minute. Six y. Y to the power 2 plus 24. So what I want you to do is, I want you to find the extreme points and to determine the nature of those points, whether they're minimum, saddle point, or maximum.
You type 2 times 3y squared. Is it correct?
2 times 3y squared, let me check.
3y squared. Then
Okay, yes, let me check my question. I feel like, let me see quickly. So the derivative of this is with respect to x, with respect to y. Six y. Nine y squared.
Maybe the last is 3y cube.
Yes, I think it's a cube. You're right. Okay, let's correct this to cube. Oh, how do we change this now?
You can cut 2. You can cut it like 2.
So this is to the power 3. Okay, you're right. So please solve this for me. And what you have to do is you have to use, obviously, the necessary and sufficient conditions to find the points and to tell what type of points they are. Hurry up.
0, 0 is the minimum point.
Okay, let me see my solution, 1 minute. 0, 0 is, how did you, what is, so what type of, what is the nature of the Hessian matrix?
6006.
6006, what's that? I'm saying whether it is a positive definite, positive semi-definite.
Positive definite, positive definite.
Okay, and what would be the, so, okay. And what are the other points? I think there are 4 points. You just got 1 point. Zero, zero is the most trivial solution. What are the other solutions?
So you mean by
-2 and
solutions,
-2 over 3.
it's determinants?
No, 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 no. See, okay. Oops. Where did this guy come from? What did I do? Okay, so what I meant is now, okay, you have this function, so you have to take the first order partial derivative. This is too thick. Let's make it thin. First order derivative with respect to x. What would this guy be? It would be 3x, x plus 2, am I right? Is equal to 0. First order partial derivative with respect to y. There are 2 variables, so you'll get 2, 3y plus 2. Am I right? Equal to 0. So xy solutions, so the solutions for this are, one is either x will be equal to 0 or this guy would be equal to 0. Y would be equal to 0 or this guy would be equal to 0. So one solution is 0, 0. The other solution is you either take 0 and this guy, which is 0 minus 2 divided by 3. The next one is minus 2 and 0, right? And the next one would be minus 2. Oops, that's not a beautiful minus 2. Minus 2 divided by 3. Okay, so you have 4 points that you get. There are 4 points at which the gradient is equal to 0. Okay, so these are the 4 points. Now, for each of these points, you have to find the Hessian and substitute these points and see what you get. Whether, so our friend said that if you have 0, 0, the Hessian, let me write it, the first Hessian or the first what leading principal minor determinant would be equal to 6, which is greater than 0, and the second guy would be equal to 36. I've solved this earlier, that's why I know the solution. So this guy would be positive definite, and since it's positive definite, this point would be a minimum point, local minimum. Okay? Now I want you to do the same for these 3 points.
The next point is, the next 2 points are maximum and the last one is minimum.
Yet. Check it correctly. Let's go with 0, minus 2, 3. What is the first, the H1? Calculate
6.
H1.
6.
6.
6.
6 is greater than 0, right? And what is H2?
Sorry.
H2 is?
-6. 12.
Minus what?
Minus 6.
No,
Minus
-6. -6.
Oh, minus 36, yeah.
Less than 0. So which state is it? Which condition is this? What type of matrix it is? Which case does it fit?
Indefinite.
Good.
Saddle point.
Indefinite. None of them.
The last
Right.
one, yes.
Good. Indefinite. So when it's indefinite, and this guy is a
Saddle point.
saddle point.
Saddle point.
Okay. Next one. Who's going to tell me then this one? -2 and 0.
Also indefinite.
H1 would be equal to minus 12.
Minus
Correct me if I'm wrong, please.
minus
Minus
6.
6.
Minus 72.
I think it's minus 6 and minus 36.
Yeah.
This is minus 6.
Yes, yes,
Are you sure?
yes.
Okay, if you're saying minus 6, I will just write it because we have no time to check. But what I'm trying to say, and this is also minus 72.
No, minus 36.
You're talking about minus 2 and minus 2 by 3. I'm talking about minus 2 and 0.
Yes, minus 2 and 0.
Minus 36.
Yes.
Okay, that's a bad mistake I made. Okay. Anyways, both of them are less than 0. Which condition does it satisfy?
Indefinite.
Okay, so this is none of them. So this guy would also be indefinite. And therefore, this guy would also be a saddle point. The last one. H1 is
Minus 6.
Minus 6.
minus 6. Okay, I'm right. And H2 is 36, or am I wrong again?
36.
Okay, I'm correct. Okay, so the first one is less than 0. Second one is greater than 0. And therefore, which condition? What is it?
Negative definite.
Good. Negative definite. The minus 1 to the power k case. And therefore, if it's negative definite, then this guy would be a
Maximum.
okay. So if you take the functional value at this point, you would see that the functional value would be 24 if you put it in here. And for the maximum point, it would be 76 divided by 9. Okay, is it clear, guys?
Oh, Professor,
Yes, sir.
for this saddle points, we don't take further derivatives as in
Yes,
our.
net. That's enough. The Sylvester test
Okay.
is more than enough. Because I mean, you don't do the third order partial derivative and all. It makes no sense. You just do this,
Okay.
and based on this, you are done. Okay.
Okay.
Good. Any questions? Okay. So now what we want to do is, so we are done with this guy, forget this guy. So far, what we have done is we have used the necessary and sufficient conditions to find possible local extreme points, right, and their nature. So these points, like you see that there's one maximum, one minimum, they're indefinite. So we have found these extreme points, and basically they are the local ones. These two conditions actually do not tell us anything about the global optimality, okay? So in order to study the global optimality, we have to know what a concave function is and what a convex function is, and we have already seen that. We know the definition of concave and convex function in terms of, if you remember, the lambda and the line connecting the points, everything under that line. So we know what a convex and concave is, okay? Now, what we want to do is we want to see how we can relate a convex or a concave function to the positive definiteness or negative definiteness of the matrix. Okay, so what I'm trying to say is that if we have a function f of, say, some x bar, where x bar is a vector, okay, of n decision variables, and we can, yes? Any question? So let this guy be a function of n variables. Then we can say that this guy is a convex function, convex, if and only if the Hessian matrix, which I denote by H, is positive semi-definite. Semi-definite. Okay, so what does it mean? That means if I obtain the Hessian matrix for this function, okay? So we want to now, and what I'm trying to tell you, I'm also trying to tell you not only the points, I'm not only trying to tell you what type of points they are, saddle, minimum, maximum, but I'm also trying to tell you whether those points are actually a global minimum or global maximum. Okay, so if you're given some interval where, for example, you have such a function, so you have this guy, then you have this guy, suppose like this, okay? So you see that at these points, the slopes would be 0, right? So we have like, this is a peak, this is a peak, this is a peak. So when you solve this equation function using the necessary and sufficient conditions, you would get all these points, okay? Even the valleys. But it will not tell you, okay, among these points, which one is the most, or the global one. We know that this is the global peak, and we know that this is the global valley or minimum point. Okay, in order to find this, so now what I'm doing is there's another extra information that we can get about the function, and that is that if the function is convex, then the Hessian would be positive semi-definite. That means the leading, what is that called? Principal minor determinants would all be greater than equal to 0, okay, for all. Okay, this is convex. Okay. Now, if the function is strictly convex, so when we say it is convex, that means there can be points, okay, there can be extreme points, okay, and there can be more than one global extreme point. That means, for example, so for this, if this is greater, that means it's convex, we could have some point, okay, let's assume that this is a very bad, just assume that this is flat over here. So this point would be a local global minimum, this point a global minimum, this point a global minimum. So all these points over here are global minimums. So even though this function is convex, okay, if it is semi-definite, then this would be the condition. All the Hessian, the leading principal minor determinants would be greater than equal to 0. And this tells us that there could be more than one global minimum. Okay. Now we say that the function f of x is, let me draw something nice over here, is strictly convex. Strictly convex. Okay. If h is positive definite. So the red corresponds to the red definition. Okay, it tells us that this is a convex function and there will be only one point, and that point would definitely be the global minimum. Okay, so that's a strictly convex. Is it clear the difference between strictly and non-strictly?
Yes.
Guys?
Yes, yes.
Okay, so similarly, you have the definition for concave. Okay, so can anyone tell me what would be the definition for concave? How can we define this for concave? So I can say that a function f of x, this is not a good color. F of x, this is a bar. Is concave. If and only if
Negative semi.
the Hessian matrix are negative semi-definite. Okay, and what does it mean? That means H1 would be less than equal to 0, and then H2 would be greater than equal to 0, and so forth until -1 to the power n of Hn would be greater equal to 0. Хорошо?
Yes.
And obviously, let's change the color, and it would be strictly, okay, concave if this guy would be negative definite. That means this equality sign is not there. Okay, so basically this is the same as if you have such a function and such a function. So this, you can have multiple maximum points. Okay, it's a plateau. Over here we have only one single maximum point. So this is strictly concave. Okay, so this is the definition that I needed to tell you guys and get it out. So if it's a strictly concave function, so any local minimum that you get in that function, that the function returns while solving the necessary and sufficient would definitely be the global. Would definitely be equal to the global minimum or maximum. Okay, so if I give you, so I gave you a function, I asked you to find the points, you found the points, I asked you to tell me whether it's a minimum or maximum or saddle point, you told me that, then I can ask you to tell me whether it's a global minimum or global maximum or global or it's just a local minimum or local maximum. So you have to use this test. And you can tell me that, okay, since there is one minimum point over here and this function is strictly, for example, convex, then therefore definitely it is a global minimum, okay? So this is a test. Is it clear, guys, everyone? Today, you guys are very quiet.
What if the matrix is indefinite?
If the matrix is indefinite, then you cannot say anything. There's nothing you can say. If it's indefinite, you cannot say anything about the function. So definitely it will not be any point. Okay, it will not be. So if it's an indefinite matrix, what does it mean? It would be some point over here or some other point over here. We don't know. Okay, so if it's an indefinite matrix, so what can we say about indefinite? I do not know what we can actually say. I cannot confirm anything for now. I know that if it is an indefinite matrix, so actually in a convex or concave. So actually, if you have a convex or concave, you'll never have an indefinite matrix because you'll have only one peak or one valley, right? Thinking about it, like, see, if you can only say a function is concave or convex, because you have to be able to draw a line such that it divides. So everything above that line, okay, should have some functional value less than any value on this line, right? So if it is indefinite, then definitely this line cuts some point, it cuts this line connecting these 2 points. That won't be the case. This won't be a concave or convex function. So you cannot say anything about the indefinite, but we can talk about the negative semi-definite and negative definite in terms of this, okay?
Okay, so we found positive definite or negative only at some point, because if it's related to X, how we can do Sylvester's test?
Come again, I did not catch your question once again, please.
You say f of X is concave.
F of X, Y, I'm talking about a two-dimensional space. It's not one-dimensional, okay?
Yeah.
Yes.
So how we do Sylvester's test if like Hessian matrix elements are variables?
So what you do is first you find the first derivative, you find the points. So when I'm giving you f of X, you take you do this necessary condition test, get the points. And then
so
you do
it's
this.
evaluated at some points, yeah?
Yes, so you calculate the points by taking the gradient. Equated to 0, you will get some points for X and Y. Just the example we saw, we found 4 points, right? And then you take each of those points and you put, so then you take the second derivative, second gradient, which would be the Hessian of the function, you would get a matrix. And then in that matrix, you got 4 points. So you substitute each point. So if, for example, for 0, 0, you substitute 0, 0 into this, you would get some value. Then you substitute the second point, then the third point and the fourth point. So you'll get 4 different points. So at these different points, you will get different Hessian matrices. And then you evaluate them and you can check. So that will, based on those points, you can tell me whether that point is a maximum or minimum. And you can also tell me whether that point is a global or local maximum or minimum. Okay.
So in order for it to be global, all of the global.
In order for it to be global, as I told you, for this guy to be global, global means yes. So in order to be global, it should be strictly, if it has to be, if you want it to be a unique global, okay, you should have a negative definite. But you
Negative
can have
definite for
multiple,
all points,
huh?
or for all points, or for one?
No, you have 4 points, right? Now you want to check whether this point is a minimum, local minimum, or global minimum, right?
Mhm.
So then you take the function, so you have to do this test. You see that if it is negative semi-definite, then it would be what we say, local minimum.
concave.
But if it is a
Mhm.
negative definite, it would be a global minimum, because in that function, for that function, okay, given function, there's only one point, and that point is the local, the global minimum. So that point is a global minimum.
Mhm.
So what you have to
Thank
do
you.
is, so based on, so, okay, you find the second Hessian, second partial derivative, second order partial derivative, you get this, you test whether it is ND, NSD, TD, PSD, and all that stuff. And based on that, you can tell whether the function is strictly or not, or it's strictly concave or not strictly, or just concave, okay? Let me put it this way. So once you have your point, then based on the Hessian nature of your, the values of your Hessian, you can tell me whether this function, without having to plot it, you can tell me whether it's just concave or strictly concave.
So my question was like, how we can tell about the whole nature of the function from several points?
How can we say about the nature of the function from several points? So let's draw this. Okay, let's say we have this function, okay? So, and we will definitely get these points, right? Am I right?
Yes, yes.
Okay. So for example, at this point, you evaluate this function, okay? So it will tell you whether this point, so the function at this point would be convex or concave. So it would definitely tell you it's a concave function, okay? Then at this point, it would definitely tell you that this is sorry, this is concave, this is convex function, okay? And then at this point, it would, now we want to check and see that whether the points that you got are local. So within this area, this would be the global. But when you took, so it depends on what is the interval of your function, okay, within what values of x and y. So I'd say, for example, x starts from 0 to 10, y starts from 0 to 20. In this area, given region, you tell me what is the local or global minimum. So you will definitely get these points. You find the Hessians, you find the functional values at these points, and then based on the functional values, you can tell which one is the global low minimum or maximum and local minimum maximum. Now, with those points, then what you can tell me is that within this point, within like between the area between two extremum points, whether that function is being concave or convex, strictly concave or convex. Okay.
So it's within some interval, yes.
Within some interval, yes, definitely. Because otherwise this
Okay.
function can go forever.
Okay, thank you.
Good. Okay, with this said, I guess, oh, wow. Okay, then you have a question, anyone? I hear someone.
Yes.
Yes, sir.
I have a question. Is it correct to say that whenever
Oh,
we have...
I Control Z.
Can you hear me?
Yes, I can hear you. I wish I wouldn't have removed it. Yes, tell me.
Is it correct to say that whenever our Hessian matrix is indefinite, then at this point we have a saddle point?
Yes.
It's always true, right?
Yes.
Thank you.
Now, let's try to, I want to quickly get this done. So we'll be talking about the steep descent method, and I want this will be included, okay? We will stop at the end of this. So even if I don't finish, you'll have to study it. It's very simple. What it says is that now what we want to do is using in a multivariate case, we want to optimize, or we want to find the minimum or maximum point. So what we have is we have a starting point, And we have a direction, okay, because we are working with vectors. So obviously vectors, they can have directions, okay. So what we do is starting from one point, we choose a direction, we move in that direction, and then after some time we evaluate the function at that point in that direction, and we see whether it is lesser than the starting point or not. If it is lesser, then that will be our new starting point. Again, we choose another direction and we move in that direction till we get to some point where the functional value would be the minimum. Okay, so this is basically known as what is this? The steepest descent method. Okay, so let's look at this and understand this using an example. Okay, so we have a starting point x naught and we have a direction, okay, which is denoted by d naught, and we have a step size. So how much should I jump in that direction? Okay, and based on this we get a new point which is x1 bar, and so x1 bar can be written as a starting point plus some scaling or jumping factor, step size, times the direction. So let's look at this example. We have a function, this, okay, where there are two decision variables, x1 and x2, and we have a starting point x naught, which is at 3, 1. And the functional value at x naught, if you put 3, 1 in this equation, it would give you 40. Okay, so we know that the functional value at this starting point is 40. Now, what we want to do is we want to move along some direction. The direction is given to us, let's say -3 and -5. So we want to move from this point along to this direction. So basically what we are doing is we are doing x1 is equal to x naught, okay, plus the direction given here, and we have some alpha. So what we want to do is now we want to know how much should I jump in this direction in order to get to a point where the functional value would be minimum than this point, that the minimum than the function value at point x naught. Okay, so I want to find this alpha, which is the step size. So what I can do is, so now my alpha is the unknown, right? So if I put in this function, I know x naught, I know d naught, I do not know alpha. So I can write the function in terms of alpha, which is my unknown variable, and then I would get this, right? So my new point would be in terms of alpha 3 minus 3 alpha, right? 3 minus 3 alpha, which is the direction, okay? And 1 minus 5 alpha, 1 minus the 5 times alpha, which is in that direction. Is it clear? Do you understand how I got this? So this is my new point, correct?
Yes.
And the functional value of this point at this point would be substituting this x and y in this function would give you this, okay? So if I substitute these 2 points in this function, it would give me this function, okay? So now I have a new point in terms of alpha, and I have the functional value at that point. Now what I want to do is minimize this, right? I want this guy to be minimum as compared to this point. Am I right, guys?
Yes, yes.
Good. So, okay, I have to clear and move down. So what I'm trying to do is I'm now trying to minimize this function with respect to alpha, because I want to find an alpha point which will take me to some point where the functional value is minimum as compared to the starting point. So if I do this, so if I want to minimize this with respect to alpha, I would get the size of alpha, which would be the minimum step size I need to jump in that direction. Okay, so basically what we have to do is we have to take the derivative of this guy because we want to find the minimum. So take the derivative of this with respect to alpha, equate it to 0 and solve for alpha. So it would give me alpha to be 0.25, blah, blah, blah. Okay, so therefore my new point would be x1 is equal to x naught, which we already had in the beginning. This guy, okay? Where is it? No. X naught plus alpha naught, which we found over here, times d, right? The d also we had it up here. Where's d? Here, okay? So when I put everything in this, in the equation, I would get this new point. So this would be my new point, the x1, okay? And the function value of this point would be, as I told you, we already know the functional value, put f of x1 in this equation, you would get the functional value, which is 5.3714. So compared to 14, we see that we have come to a point where the function value is lower, okay? And what we do is, then afterwards, what we can do is then at this point, when alpha is equal to 0, so you take the derivative of f of alpha, okay? And then afterwards, you put alpha is equal to 0, okay? So take the derivative of this guy. So what is the derivative of this guy, this equation? Someone tell me quickly. Derivative of this with respect to alpha.
-2.
Derivative of f of alpha with respect to alpha would be,
-6.
let me do it, -6 plus 10, 1 minus 5, alpha times -5 minus 50. And if I put alpha is equal to 0, this would be -18. -18 -68, am I right?
Yes.
Okay, so when I put, oh, I've written it over here. I did not see this. Okay, yes, I'm right. So when you find this, it would be -68, right? Now, what we want to do is, the other test is that you can take the derivative at this point. Okay, that means you're at some point x naught, and the derivative would give you the direction, okay, of increase, and you multiply it with the direction. So if I had 610, okay, which is the gradient at point x naught of the function, and you multiply it with the distance that I'd given you, which is this guy, okay, and you would see that it would give us the same thing, okay. So this means that, what does it mean? Can anyone tell me? Let me see if you guys can tell me.
What do you mean?
What is this? How is it that these two are the same?
While substituting the alpha 0 into the derivative of f function, we get -68, which gives us the intersection point with like derivative of f function, and this gives like the multiplication of f of x naught to direction.
So the product of the gradient at a point x naught at your initial point with the direction in which you're moving, okay, so it is -68, and this -68 is actually the value of the function of the first derivative of the function in terms of alpha, where alpha is equal to 0, right? So what does it tell us? It tells us that the gradient, where is that guy? I had a figure somewhere. The gradient is always perpendicular to what is this blue line?
Tangent.
Tangent, right? So that means this guy will always be pointing to the direction in which the function is increasing. That is what it means. Do you understand that? So at any point, if you take the gradient at that point, it would always point in the direction in which the function is increasing. I've written it over here. So the gradient at a point points in the direction of the increasing function value. And it is always perpendicular to the tangent passing through that point. Okay? Or in other words, you can do this. So this is what it means. So basically, the direction, search direction, would be a unit vector in the direction of the gradient, negative of the gradient. And the reason why I put this negative is because this is a descent search, and we are looking for the minimum, not the maximum. Since this guy is always increasing the functional value, I want to find the minimum. So I have to go in the opposite direction, and therefore I should go this way. And to go this way, I just have to put a negative gradient, right?
Yes.
Is it clear, everyone? You see, so functional value is 3, 5, 7. So this goes in the increasing order, but I want to find the minimum. So minimum obviously will be that the functional value is low. So we go in the exactly 180-degree opposite, which would be the negative of this. And so we choose our direction, the dk, always in a way that it would be negative. And what we have, where is that guy? What we have over here in your Cauchy method or steepest descent method is what you do is you first have a point, okay? You find the gradient at that point. You have a function, you have a point, you find the gradient at that point. Then you find the direction in which you want to search for the new point, and that would be exactly the direction, the opposite of that of the gradient. And this is actually normalizing it, okay? So this is the normalized direction, where this is the Euclidean norm. You know the Euclidean norm, right? Square root of x1 square plus x2 square plus xn square, okay? Is it clear, guys?
Yes.
Good. So the descent, so in the steepest descent method, what you want to do is you want to move in the direction where the function is reducing. So what we have is that the gradient will always give us a direction which the function is increasing. But since we want to find the minimum, we put a minus in front of it and we move in the opposite direction. Okay, so we have our direction now. Okay, so now we find this alpha naught. How do we find alpha naught? Just like in the example we had. If we have to find alpha naught, that would minimize this function, right? And this function is our new point. We know d naught, we know x naught, we want to find this alpha naught, okay? And therefore, based on that, we find this alpha, and then we substitute it. This would give us a new functional value and a new point, which is x1. And we check the condition, whether this functional value at this point is, very close to 0 or or not, the termination condition. And if it is not, then you again repeat it. If it is, then you stop. Is it clear? Everyone? Anyone? Timur, is it clear? Yet. Yarasil, is it clear, sir? Tamerlan, Sultan.
I think yes, it is clear.
Good, Marat. Good.
Yes. Yes.
Good, Didar.
Yes.
Bebaris.
Yeah.
Daniar.
I've already said.
Oh, you said it. Okay. Okay. Barjan.
Yeah, it seems okay.
We don't have any. Okay. Aigerim.
Yes,
Good. Are you the only female student?
I think yes.
Oh, good. Very good. Asad.
Yes, it's clear.
Good. I'm glad. So what we have till our midterm is till the end of the steep and descent method. So just to give you a hint of what type of questions you will expect, I'll give you a function, I'll give you a starting point. I'll ask you to do a number of iterations and apply steep and descent method. Or I can actually ask you to find the maximum. In that case, you will have steep and ascent method. And ascent method means you will not be having this minus sign, right? Because we are moving towards the maximization of the function, and the gradient always will show us that direction. So we do not have to negate it. Okay. So if it's a maximized, remove this. If it's minimized, you put a minus sign. Is it clear, guys?
Yes.
If you get the concept,
Yes.
actually playing with this is all you should know is you should know the concept of how to attack the problem, and based on that you can do it. Okay. Then after that, forget about all this. So I told you how to choose your. So there are some examples. So like example 3, it will help you out. Please work it out. Okay. Okay, then we have this exact line search where you do not have to worry about this. We can skip this. The Wolf's condition is again very mathematical Goldstein conditions. Actually, I had studied this when I was in my undergrad, but now when I'm looking at the lectures for undergrad course on numerical optimization, they do not talk about this. So I would also say that let's skip it, okay? So the convergence. So if you actually look at the steepest method, so let's look at it visually. So if you start at this point, it's going towards the maximum. So the perpendicular, so the gradient will be perpendicular to the tangent. So it will be going here. And then at this point, so it will give me some, so the alpha over here that we get, which gives us this function value is obtained. So we stop here. Again, from here, we draw the perpendicular line to the tangent at this point, which is this line. And again, we stop here and we keep doing this. So you see it has a zigzag motion, okay? So for this is actually the behavior of the steepest descent method for this function given over here. And then as you see that the convergence towards the minimum actually slows down as you approach the minimum point. Okay, so if you say the minimum some point over here, in the beginning, it takes big steps, so it converges faster. But as you kind of, approach the minimum point, the zigzag motion becomes very slow. So this is one of the drawbacks of the steepest method. Okay. I have added a supplementary file. If you look at that, there is an explanation on how to actually overcome the steepest method and how instead. So basically, if anyone who is a very keen and very attentive listener or reader, you would see that, okay, what happens if instead of doing it in a zigzag manner, I just connect the points, these points, and just go in that direction, right? So I do this, I do this, I do this, I do this. So I get these points and I just draw a line and go there. You see that this would also converge much faster rather than doing this zigzag approach. Okay, so this is explained in the supplementary file with lots of examples actually. So look at that supplementary file and I think it would help you. So instead of going this way, what we can do is we can just, and this is known as the Powell's method. If you read that slide, you will see it. Powell's method. I think Pavel is a Russian name. I'm not sure. Is it a Russian name? It sounds Russian to me.
No.
Pavel? Pavel, no?
Pavel, maybe. Yeah.
In Russian, it's Pavel.
Yeah, Pavel. Well, the English name that they have written it as Powell. So Pavel guy, that guy, he was a very smart guy. So he said, instead of doing the zigzag thing and using the gradient at each point, so you don't actually even have to find the gradient. So every time you see, you have to find the gradient. So just finding the gradient is finding the derivative. And your function is, for example, some complex function derivative, finding the gradient may not be an easy job as well. So I said that in the beginning, if you just have these points, what we do is just connect the points and move in that direction. So obviously that would take us to the minimum point, right? So read that slide, please. And that's it. So for Tuesday, I will see you will have your midterm. Questions will be on Moodle. Please come on time and make sure you finish on time. And everything that we studied till today, including today, will be included in your midterm. Read the questions very carefully. Okay, guys? Any questions? If you have any questions till then, you can email me and I will try to answer you.
Sorry, in the midterm, how many questions?
No idea. I have to sleep tonight and it has to come to my dream. I have no idea.
Okay.
I have to dream. Okay.